and PBQ are drawn to intersect the circles at AD, P, and Q respectively. So, okay. So, like two lines have been made of this. Let's say something like this. This is A. This point here is D. Please make this figure. And then this. Okay, so this point here is. Hmm, it's somehow not crossing. Okay, oops, sorry. Kind of like this has to be B in that case. This is ABD. I've made it very differently. Give me for that. This is AC. Here we have what is this? Just a minute. Hmm. Okay. This point here is P. Then they have made a Q. Whoops. This PBQ is going like this. Q, and here we have joined it with C. Okay, plenty of line segments. Now what do we have to do in this? Prove that angle ACP is equal to triangle angle QCD. Okay. Okay. So nothing else is given apart from this. Okay, we just have to show that angle ACP is equal to angle QCD. That's all we need to show. And nothing else is given in the question. This is to intersect, blah, blah. Okay. So here, what all do we have? We have, let's say the bigger circle. Let's call it circle 1. Okay, let's call this circle 1 and let's call this circle 2. So you can see in the bigger circle, if you look at this chord BC, if you look at, no, not chord BC, if you look at this chord, if you look at this chord AC, Yes. Or rather, if you look at the chord, okay, look at the chord AP. AP. Okay. Look at the chord AP. We need to show that angle ACP, this angle, is equal to angle QCD, this angle. Okay. Now, this angle over here, ACP, will be equal to which angle? It will be equal to, if you look at this chord, okay, then this chord is making two angles, right? It's subtending this angle here. This is A, this is B, this is point C, and this is point B. Okay, so it is subtending angle ACP, this one, and angle ABP, this one. So we know that these two angles are going to be equal. Why? Because they are angles in the same segment, right? Angles in the same segment are equal. So because of this chord AP, it is subtending two angles, this one angle ACP and angle ABP. So this angle will be equal to this angle because angles in the same segment are equal. So I know it will be a little difficult for you to see it in this figure. So that's why I've drawn another figure separately. This is B and this is C. Okay. So in circle 1, angle ACP is equal to, or think of it like this, chord AP subtends two angles at C and B. Okay. And what are those two angles? Therefore, angle ACP, this one here you can see that angle ACP is equal to angle ABP. This one here, you can see in the other figure, that will be more easy. That will be easier for you to understand, angle ABP. Okay, and in the bracket you will write the reason, since angles in the same segment are equal. Same segment means this entire portion is a segment of the circle, right? We have already discussed this in the previous class. And if any of you have missed any of the classes, I would suggest you to please go through the recordings before you come to the next class so that you won't be like, oh, what is going on? You won't be all lost. Okay. So please go through the recordings before coming to the class. Angles in the same segment are equal. Now, similarly, or rather, you can look at these two lines. Look at these two lines. Here you have one line. I should have made this color. Look at this line, the yellow one, or you can say the one which I've highlighted in yellow. Okay, this one, this line. And look at this line. These two are straight lines. And so hence this angle and this angle will be vertically opposite angles. What are vertically opposite angles? They are angles formed when two lines intersect each other and there is an X forming. So these two angles will always be equal. We know that they are vertically opposite angles. Also, angle ABP is equal to angle, what is this? QBD. QBD. Vertically opposite angles. Or let's write the full form. Okay. Now in triangle, in circle 2, meaning the smaller circle. In circle 2, again look at the circle, it's going to be like this. This is your point Q, this is your point D. These two, you can join them to make a chord. Here is your point B and here is your point C. This is forming an angle over here from D to B. You can see from D to B and from B to Q. Then from D to C and from C to Q. So you can see the two angles are being formed, this one and this one. And these two angles are going to be equal because same reason, angles in the same segment are equal. So in circle 2, angle this one, the angle at B, what is that called? Angle DBQ or QBD, angle QBD. Let's name this equation 1, let's name this equation 2. QBD is equal to angle ABP. No, what is this? This is angle QCD, right? QCD. QCD. Hmm. Angle QBD, this one, is equal to angle QCD, this one. So these two angles are equal. So here you can see from first equation, angle ACP is equal to angle ABP. You know, if you say X is equal to Y is equal to Z, and Z is equal to T. Then from these three things, what can you say? You can say that X is equal to T, right? So from these three equations, ACP is equal to ABP, and this ABP is equal to QBD. And now this QBD is equal to QCD. So that is why ACP and QCD are the same, are equal. Okay. So from equation 1, 2, and 3, angle ACP, the one we started with, is equal to angle QCD. Hence proof. That's what we needed to prove. You guys had told me once what all chapters have been done in your class. Acha, okay, I have the list. I think quadrilaterals is done, right? Namrata ma'am completed quadrilaterals?
Yes, ma'am.
Yes, okay, fine. Okay, so I hope you've done writing this. Next, question number 10. If circles are drawn taking two sides of a triangle as diameters, then prove that the point of intersection of these circles lies on the third side. Okay. So if two circles are drawn taking two sides of a triangle as diameters. So let's draw, and they're not saying what kind of triangle. So you don't necessarily have to draw an isosceles or an equilateral triangle. You can just draw any random triangle. So let's not draw too big a triangle, otherwise the circle will get really huge. Okay. So this one here, there will be a circle. Weird circle. Okay. And the other one is this. Okay. So this is the point, let's say A. This point, let's call it B. This point, let's call it C. Okay. Fine. And we have to prove that the point of intersection of these two circles lies on the third side. So construction, we are gonna have to do construction here. Construction. Join AD. Join AD. So if we are to show that it lies on, if you're supposed to show that a particular point lies on a line. So see, if you have a line over here, and if you have this point, let's call this is B, this is D, and this is C. Let's say you need to prove that this point is on BC. The point B is on the line BC. If you need to show that, then what you can do is you can find this angle. Okay, let's say something you have over here. You can find this angle and this angle. If the sum of these angles is exactly 180 degrees, that means it lies on the line. Otherwise, it won't be 180 degrees. See over here, the sum of these two angles is greater than 180, right? So let's say the point D is somewhere over here. Then again, the sum of this angle and this angle will be not equal to 180. It will be less than 180. Or in this case, it is greater than 180, the sum of these two angles. So if the point lies exactly on the line, then the sum of this angle and this angle, the sum of these two angles will be exactly 180 degrees. So in order to show that point D lies on BC, we can show that the sum of these two angles, which two angles? BDA and ADC. So to show that D is, or D lies on BC, we shall show that angle BDA plus angle ADC is equal to 180 degrees. Okay. Now, let's start with the solution. So we'll write it like this. So we need to show that this angle plus this angle is 180 degrees. Now see, look at the circle, the pink circle. Okay, look at the pink circle. In the pink circle, okay, in the pink circle, okay, undo, just a minute. Okay, so it's like this. This is your B, D, A. Okay, I have drawn it once again just so you can understand what's happening because the figure is quite cluttered. So you can see that AB, which is the diameter, is also a chord, right? And it is subtending this angle at point D. And we know that the angle subtended by diameter is always 90 degrees. So uh, in the first circle, or you can say since AB is diameter, therefore it subtends an angle of 90 degrees at any point on the circle, right? And D is a point on the circle. Therefore, angle BDA, this one over here, is going to be 90 degrees, is equal to 90 degrees. Similarly, since, now look at the other circle, the green circle, since AC is diameter of the other circle, therefore, angle ADC is equal to 90 degrees. This one is also going to be 90 degrees because same reason for the other circle, for the green circle. Okay. Therefore, angle BDA plus angle ADC is what? 90 plus 90 is equal to 180 degrees. That implies D, or you can say BDC, is a straight line. That implies D lies on BC. Done. Please write this quickly. All right. Let's move on to the next one. So here, if triangle ABC and triangle ADC are two right angle triangles with common hypotenuse AC, then prove that angle CAD is equal to angle CBD. Figure is given? No. ठीक है. Fine. So if A, B, C. So what I'm going to do first is, since this is the circles chapter, there's obviously going to be a circle involved here. So I'm first going to draw a circle, and I'm going to erase this later. If you want, you can also draw this. Up to you. So if A, so this is A, B, C. This is a right angle triangle, and ADC are two right angle triangles with common hypotenuse AC. So again, there has to be a 90 degrees here, a right angled triangle. Whoops. Okay, 90 degrees are two right angle triangles with common hypotenuse AC. Then prove that, to show that. Too huge. Why did I draw such a huge one? Okay. To show that angle CAD is equal to angle CBD. This is what we need to show. Now see, this one is 90 and this one is 90. What is given? Given angle B is equal to, or let's write it like this, angle ABC is equal to 90 degrees, and angle ADC is also 90 degrees. Okay. So if these two are 90, solution. Angle ABC plus angle ADC is equal to 90 plus 90, which is 180, right? So what are we observing here? That the sum of two opposite angles in this quadrilateral is 180. That means this quadrilateral is cyclic. Yeah. Therefore, ABCD is a cyclic quadrilateral. Because sum of opposite angles is 180. We'll actually have to show the same for these two as well. Let's do that. So let's take a look at, we have to show that angle CAD, this angle is equal to angle CBD. Achha, okay. Have to make this one CBD, this angle. Okay. So before that, first we need to show that. Okay, just a minute. Let's not write this yet. Don't write this yet, okay? Fine. So in a cyclic quadrilateral, to show that this quadrilateral is a cyclic quadrilateral, you need to show that each pair of opposite sides is 180, right? Not just one. So this one plus this one is 180. That way we can clearly see from the question itself. But we also need to show that this one plus this one, the sum of these two is also 180. So that is also very clear. It is very obvious, but let's do it anyway. So uh, also angle what is this angle, this one, what will it be called? DAB, angle DAB, this entire angle, okay? Plus, so now we are saying the sum of all the angles of a quadrilateral is 360, right? Angle DAB plus angle ABC, this one, plus angle BCD, this one, plus angle CDA, this one, the last one, is equal to how much? 360. Why? Because angle sum property of a quadrilateral. The sum of all the angles of a quadrilateral is 360. And now we know that ABC plus CDA or ADC, same thing, okay, is 180. So let's call this equation 1. That means angle DAB plus angle BCD plus this much, this plus this. What is this plus this? It is 180 as per the first equation is equal to 360. So now the 180 goes to the other side. Angle DAB plus angle BCD is equal to 360 minus 180, which is 180. So we have shown that sum of opposite angles, see DAB is what? This one. This one is DAB and BCD is this one. So sum of opposite angles is 180 we have shown. So from equation 1 and 2, sum of opposite angles of quadrilateral ABCD is 180 degrees. Therefore, ABCD is a cyclic quadrilateral. Okay. Now the next part is very simple. You just have to show that angle CAD, which is this one, angle CAD is equal to angle CBD. CBD is this one. That's all you need to show now. So if it is a cyclic quadrilateral, that means we can draw a circle around it. So consider chord DC. Consider the chord DC. Okay. And this chord subtends two angles. One angle it is subtending at point B and one angle it is subtending at point A. So these two angles are going to be equal because angles in the same segment are equal. It subtends it subtends angles at points A and B, which what are we talking about? Chord DC, okay? It subtends angles at points A and B. Therefore, angle CAD is equal to angle CBD. Reason? Angles in the same segment are equal. Okay. So just ignore this part. Okay. If you have something like this, a chord is subtending two angles in the same segment of the circle. Segment means the part that a chord makes. This portion is called a segment. This is a major segment and this is a minor segment. So angles in the same segment, they are both in the same segment, right? Which one is the other segment? This is the other segment. So these two angles will be equal. Angles in the same segment are equal, and we even proved it. So this proves the question. Yeah. Next question, prove that a cyclic parallelogram is a rectangle. So you have been given a cyclic parallelogram. Okay. So what is given? It is given to us that number one, ABCD is a parallelogram. Okay, because parallelogram means it has some special characteristics. And the second thing that is given is ABCD is cyclic. So cyclic has its other special characteristics. Okay. So now let's start with the solution. What do we have to show? To show that ABCD is a rectangle. Now, to show a rectangle, see, if you have a parallelogram whose one angle is 90, that means it is a rectangle, right? Why? Because see, when you have a parallelogram, and if this angle is 90, let's say, if just one angle is 90, then we know that in a parallelogram, opposite angles are equal, so this will also be 90. And we know that in a parallelogram, adjacent angles are supplementary. That means this angle plus this angle should sum up to 180 degrees. And what is the supplement of 90? That is also 90. And so if this is 90, this also has to be 90 because opposite angles in a parallelogram are equal. So if you have a parallelogram and you have just one angle is equal to 90, that means the entire parallelogram becomes a rectangle. Okay. So now you will write since solution. Since ABCD is a parallelogram, therefore opposite angles are equal. Fine. So now we don't know which angle is what. So we will say therefore angle D is equal to angle B is equal to X, say. Okay. So opposite angles are equal in a parallelogram, right? We know that in a parallelogram, opposite sides are equal and parallel, and opposite angles are equal. X, say. Also, since ABCD is cyclic, which is given in the question, therefore, what is the speciality of cyclic quadrilaterals? Opposite angles are supplementary. Therefore, angle D plus angle B will be equal to 180 degrees. That implies X plus X is equal to 180 degrees because D and B are X, right? That means X plus X is what? 2X is equal to 180 degrees. X is equal to 90 degrees. So that means ABCD is a rectangle. Okay. Let's do some more questions. Hmm. Hmm. Okay, let's do this question. This is an extra question. ABCD is a parallelogram. The circle through A, B, and C intersects CD produced if necessary at E. Prove that AE is equal to AD. Just a minute, I'll draw this. So this is the circle. Whoops. Okay. So this is the circle, and ABCD is a parallelogram. If it's a parallelogram, so this is A, B, C, D. I have not drawn a perfect diagram. It's okay. You just have to draw a rough one in your exam. A, B, C, D given. A, B, C, D is what? A parallelogram. And A, B, C, E is a cyclic quadrilateral. A, B, C, E is a cyclic quadrilateral. So what is happening here is ABCD is a parallelogram and you're just extending the side CD. You're just extending it. It's called producing. CD produced at E. Okay, it is intersecting the circle at this point, right? So this is E. So ABCE is a cyclic quadrilateral. It's not a parallelogram, obviously, but it's a cyclic quadrilateral. You need to show that AD equals AE. Okay. So clearly since this is a parallelogram, so first of all, let's see what we are going to do here. Since this is a parallelogram, so this angle plus this angle, sorry, this angle is going to be equal to this angle. So let's say this is X, this is also going to be equal to X. But since this is the ABCE is a cyclic quadrilateral. Now ignore this one for a bit. Since ABCE is a cyclic quadrilateral, so now this angle X over here at B, this angle plus this angle will be 180. So this angle will be 180 minus E. Sorry, 180 minus X. Which angle? This one. The angle formed at E will be 180 minus X. Okay. So let's restore what we deleted. So this angle over here is going to be 180 minus X. Okay. Mm. Just a minute. Okay. Mm. So AED plus angle ABC is 180. Okay. Angle E. Huh? Acha, one more thing. Look at this angle. Look at this angle over here. This one. How much is this going to be? Look at this. It's like this is your D, this is E, and here is somewhere over here you have C. Okay. And here you have A. So if this angle is X, how much is this angle going to be? It's going to be 180 minus X, right? It's going to be 180 minus X because this is a straight line. So this is going to be 180 minus X. So let's write it. So this one will be 180 minus X. So you can see in this triangle ADE, both these angles are 180 minus X, 180 minus X. So that means it is an isosceles triangle, right? If in a triangle you have two angles are equal to each other, that means sides opposite to equal angles are equal. So these two sides will be equal. So let's write it in a systematic way. Since ABCD is a parallelogram, therefore angle ABC is equal to angle ADC is equal to X, say. And in the bracket, we will write the reason that opposite angles of a parallelogram are equal. Now, so there are three steps in this problem. First one is writing them both as X. Now, since ABCE is a cyclic quadrilateral, therefore, angle ABC plus angle CEA is equal to 180 degrees. CEA bole to this angle over here. Okay, is equal to 180 degrees since opposite angles of a cyclic quadrilateral are supplementary. Okay, so now ABC we had written it as equal to X, right? So that means X plus angle CEA is equal to 180 degrees. You can write it simply as angle E also. So X plus angle E. So that means angle CEA is 180 minus X. Now remember this. We'll mark it as equation number 1. Then the third step. Now, angle EDA plus angle CDA is equal to 180 degrees. Reason? Linear pair. So that implies angle EDA, which is the angle that is formed at D, okay? This angle over here, this angle. Tiny one, which you're not able to see probably. Angle EDA is equal to 180 minus CDA. And what is CDA? That is X. 180 minus X. From 1 and 2, angle CEA is equal to angle EDA. That means triangle ADE is isosceles with AD is equal to AE. Reason? Opposite, no, uh, sides opposite to equal angles in a triangle are equal. And with this, you're done. And with this, we are also done with the chapter circles.